Hello, everyone. Good afternoon, good morning, and good evening, depending on where you're listening from. So, my name is Jesus Lestin Donald, and today I'll be taking you through simulation. I think it's due time, right? Now, I over the years, I've noticed that the courses we have on YouTube and for learning fail to actually recognize one important fact, and which is actually simulating something that people can relate to. Now, simulation is validation. We all know that, but we have this difficulty when it comes to translating what we know and what is actually needed. You understand? So now this is an attempt to reconcile, the fast edge of simulation and its complexities and bringing it closer to something easily understandable. Okay, now today, I basically want to welcome you guys to a definitive exploration of mechanical endurance and structural survivability. Okay, now in the field of mechanical design, the we are constantly balancing the raw properties of materials against the physical layouts of its geometry. And what this video is basically gonna do is I provide a step-by-step breakdown of this a very rigorous finite element analysis, right? So now we'll be going through four levels of impact or four very detailed scenarios, very distinct and very detailed that will transition us from basically basic human kinetics into we'll just start escalating and escalating the trauma on the steel on the 3 millimeter security door, and then we'll see how much it actually affects it. Okay, good. Now for this simulation, we'll be working with a 3 millimeter structural architecture. Right now, for context, simulation is very easy. That's how I put it. Simulation process, especially when you're simulating with SolidWorks, is really predictable, right? It's a very straightforward process. All you have to do is know the steps. Now, the first thing you should do as an engineer simulating, the first thing is to determine your geometry. Now, your geometry is basically we saying you trying to make it less complicated and remove parts that are not important to your simulation, right? For instance, fillets, edges, chamfers, whatever it is that will not be 100% valuable and will not alter the results of your simulation needs to go right now. For this design, I have already done the necessary. I have a 3 millimeter steel door, the frames are there and everything, so I'm basically trying to I've done the geometry part, which is me modeling it. So my geometry, I focused on the simplicity of it all while I was modeling. And then if you notice at the doors, if you notice, we have some sort of Z reinforcement on the back. Now, this is because in real life, we're trying to mimic a real life situation. In real life, the doors doesn't just isn't just plain steel, because if it's just plain steel, then we run into issues where we have to, the deformation remains like a plastic, it bulges in and it bulges out. So we reinforce it to mimic um, real life. Okay, now, so then after your geometry, your next step is obviously choosing your material, right? Now, choosing of material, it's a personal choice, right? You have to weigh the pros and the cons and what's what, right? Now, material goes, since it's an engineer's choice to pick any material they want. For this material, we'll be going, I preferred the ASTM A36 structural steel, mild carbon steel. Now, for context, in case you don't understand, the AMST is one of the most widely used and dependable specifications for carbon structures. Right now, ASTM is basically us telling us is an international standard for the American Society of Testing and Material. Now, those are not important. That's just okay, the international standard. Then the A right there tells you that this material is a ferrous material, right? Now, then the 36 at the back tells you, which is actually the most important part, it tells you the yield strength. It's 36 kilopounds per square inch or approximately 250 megapascals. right? So now we know our material. The next thing to do is to actually, now let's talk about the threshold. Okay, we've talked about the threshold, ultimate tensile. So these are just properties of the materials themselves, right? Now the setup, the what I was saying now, the door is a 200 by 900 millimeter security door. So basically, we know it's an average sized door, huge door, right? Now, since let's say our first scenarios now, let's talk about the first scenario now. The first scenario is human punch. Second scenario, same human punch but a heavyweight boxer. And then third scenario, a military battering ram. And then the fourth scenario would be a car, high speed impact vehicle. Okay, now let's talk about the human punch. Now, human punch, as human punch goes, human punch depends solely on the uh, the the person in question, right? Now, for this, we are mimicking an average untrained adult, somebody that isn't really, trained, right? Somebody very simple, okay? And the person balls up his fist and punches the door. That's what we're simulating at first, right? Then for the second simulation, we'll be talking about if someone who's trained, right? Someone who actually throws and punches for a living. You understand? And then the third, we'll be looking like a battering ram, where we have like three or two police officers, hitting the doors themselves. You understand? Right now, let's then for the low impact vehicle, we'll be simulating the car slamming into it. Right now, because the door thickness is 3 millimeters, you have to know that it's going to act like a thick wall, a very brutal thick wall now. And then for these four scenarios, we'll now walk through them. Now, let's start with the first scenarios. Now, for the first scenarios, in physics, now basically, in terms of physics, the untrained human being throws what engineers basically call arm punch, right? This is not a trained punch, it's just you throwing your punch and then slamming your hands into it, right? Delivering basically have at an average 800 newtons of force. Okay, now without any external support, without any, just basically punching. Now the first thing we do for simulation is this: we've chosen our material, we've taken our geometry. It's a 2000 by 900 millimeter door. Now the first thing to do is to actually apply your fixtures, right? Your fixtures is telling you how fixed is your design, how are you keeping it straight. Is it going to be hinged, cemented to the wall? We're talking about the frames of the door, right? Now if you notice, I framed the entire edge because I don't want it to budge, right? Straightforward, select your entire edges and then just fix them up. Okay, and then we apply force, right? Now when it comes to forces, because the human arm is about it's circular in nature. So what we did is we mimic a circular arm, right? A situation where you ball up your fix, and your fix is about, an average human fix is about 80 millimeters round, right? We put a 80 millimeter circle there. Now to get a circle, it's basically easy. Using your split line, draw a circle, use your split line, select the face and project it there, and you get your circular sorting. So you can actually select it when you're applying force. And then what we do is we now go to apply our force, and then we apply what's it called, our force, right? Apply your force and then it's done. And then the next step is to mesh. So basically, if you're new to what meshing is basically you splitting. Now simulation is a mathematical model trying to figure out what's going on, right? Now, since it cannot figure out what's going on in its entirety, what it does is it actually splits the machine into, it splits the part you're trying to simulate into smaller parts, right? Now, if you notice these meshes, if you see the splitting of these meshes, it's a bit large, right? Now that's because we are going with basically default meshing. We are not trying to alter. And if you notice, you'll see that places where it actually needs much more concentration, it actually becomes tiny and focuses on that area. Okay. Now we now have to, basically, the human hand as punching is having to rely on pure velocity, right? You just punch with their whole weight, like 5% of their weight, and then just slams into the door. And then you run your simulation. Now, for simulation is a fun way. Now, looking at this, we can obviously see the impact we have on the door, right? Now, how do you know this? Now, for instance, now first things first, without any external support, the results is going to be disastrous, right? This is a human being slamming his hand to the wall, obviously, right? Now, because the use strength of this standard A36 steel is exactly 250 megapascals, the amateur punch doesn't even crosses any line. He just leaves. He doesn't even leave a permanent dent on the door, right? Even he just basically punches and then immediately the hand goes right. Now you see our forces there. Our maximum stress there is about 34 point approximately 35 megapascals, right? And then the huge strength of the material, that is the huge strength, is the point before it actually fails, before it actually starts deforming plastically, not elastically. If it deforms elastically, it reverts back to its original position, right? Now before it starts what's it called, before it actually starts deforming elastically, you notice that we got a 34 let's say 35 megapascals, right? Now this is basically concentrated inside the what's it called, the circle. So it's basically, you see it's a yellow dot there, but it doesn't really do any damage to the door, right? And then when we look at the displacement, you notice for the displacement, obviously there's going to be some sort of displacement, but it's going to be elastic, because even at that level of it's going to just bulge back and then it's going to come back in. And then we have a factor of safety of 7.2. What factor of safety means is basically, factor of safety tells you how safe a product is, right? Now, for factor of safety of 7.2, it tells you this dog could withstand 7 times the human punch. If you multiply the what's it called, the force we used, multiply it times 7, what's the before you would be able to even make a dent on the door, or like punch the door. And then what we have is the person's arms is broken, and then that's just it. You just have to clean it off and take the person to the hospital, because the arm is definitely gonna be broken, right? Good. Now let's talk scenario two. Now scenario two is quite different, right? Now for scenario two, what we basically doing is we are now we've optimized our rib, we've done the whole simulation, so we are not really doing that much, right? We are trying to actually simulate a professional athlete driving an explosive 3,000 explosive 3,000 punch, right? A massive 600% increase over the amateur who just punches with his entire strength without being training. Now, of course, now the door is obviously gonna get smashed. That's what we're thinking, right? Now, if we convert this 3,000 newtons to a dynamic impact, you see it's roughly 5-10 kilograms, and then you just press it over the circle, because the circle is the bulge where we're actually putting. So it's basically, let me just put it in perspective. It's like taking a full-grown grizzly bear and punching it. And of course, we've seen these heavyweights, people that actually do punches, right? So they're really, really terrifying. So when you see them punching and punching and punching, now imagine them punching this door. Now we're not taking into account bones, pain level and all that. We're just saying just slam into it, right? And then when you do that, we see a result that almost slightly looks the same. Now, for context, right? If you want to really, really understand, my point is to pay full attention to the deformations. Deformations comes in form of displacement. It tells you whether if they actually, and the percentage of which they actually, bulge, right? It's a 3 millimeter, what's it called? It's a 3 millimeter steel, right? So for the first instance where it bulged on point eight or something, it's a bit of a fraction. It doesn't really make much impact, right? Now, scenario two, we see that the von Mises stress peaks at about 118, basically approximately 119 megapascal. So that's not really enough to actually uh, damage the door, but I think we get some sort of like deformation. You understand now, because now the maximum stress there, 119 is safely below 250, right? But it still won't create a massive crater. You will just get a kind of like a microscopic or a tiny dent on it. You understand? A brief dent on it, but it's not going to have as much impact as other scenarios would be, right? Now we are because this value is safely below our 200 degrees, so the material remains entirely balanced, and then it's just basically what it just means is I don't know if the hand of the boxer is gonna snap, but it doesn't really make any dent. And then if you look at the if you take a look at the displacement, you see that it displaces approximately 1.3 meters. 1.3 meters is almost half of the what's it called? Almost half of the thickness of the door. So of course, it's gonna cause like a catastrophic career-ending fracture for the person. Like the hand is gonna just go right. Good. Now that's for scenario two, right? Now let's go to scenario three. Now for scenario three, with scenario three, we are now moving basically out of human anatomy. We've seen the extent of how much humans can actually, go. Now, for our final, for what we're just trying to simulate now is we'll just leave it to two human beings taking the ram and then slamming it to the door. And then if there's one thing we should take into account is because a ram, the ramming size of the size of the ramming batter won't be as small as the human punch. So, in my opinion, right, in my opinion, the area covered by the arms plays a lot of factor. It plays a lot of role. It factors a lot in the final results we get, right? Because it's logical to assume that because of how big the arms are, right? They should actually the bigger the arm, the more surface area it covers and the more impact it makes. Right now, for an average, if you check an average battering ram is about 125 to 150 millimeters. So I'm going with a minimum 125 millimeter for the battery ram. So what I do is that I increase my surface area for force to like account for that, roughly 4 inches to 5 inches, and then we now deal a battering force of 12,000 Newton. Now, 12,000 Newton sounds like a lot. I mean, these are the kind of, these are the kind of like that actually slams a door open. Now, we should take into account that the doors do not, for this door simulation, we are not working with hinges. So the door and SolidWorks won't allow the simulated door to like, slam open. What it's going to do is going to simulate, it's not going to simulate tearing because of some technical, that because it's just, it's not trying to evaluate. It's going to assume it's going to expand infinitely, but it's going to tell you that it is at this point that it actually breaks. Okay, now we are discovering the material's true strength, right? So now, if you look at the results, now you see that the yield strength is way above 250, right? It's already slammed. It's already so the door is basically slammed, right? And then it shows like this. This, if you notice, look at the what's it called, the legend there. You see that it has like this catastrophic spike where you see that the energy doesn't it just it basically the door cannot really absorb most of the energies there. It just slams through. And then most importantly, now if you look at the displacement and the deformation, you totally see that it's goes through at least basically 5 millimeters into it, right? Creates a massive acoustic boom and just goes inside, forcing the shockwave to our entire structure. It spreads. You see, it spreads across. And then when you look at the stress, you see it's basically see some patches of yellow, and then you see the amount of forces and how far it actually goes. Now, there's one thing to note, right? We are trying to simulate and see how it actually applies in real life, and that is quite important to note because when you look at the mass there, right, when you look at the maximum when you look at the maximum force, you notice is at the edge, right? We are simulating a whole scenario, everything is joined together, and then we fix it and we slam it into the I see that the place shining red at the edge is where it's going to first, you know where it's going to start tearing from, not really even from the middle. It's going to bulge from that place and then basically obliterates the yield stress, blows right past the material's ultimate stress, the tensile stress. It's 12,000 pounds is two grown ass police officers hitting it, and then in real world, this causes basically immediate material failure, and in the face of that, it tears the door into pieces, right? So now we've gotten and achieved our final. We've achieved at least a catastrophic situation, right? Now an attempt to actually simulate and tell you how it actually does in real life. Okay, now let's go to our final scenario. Now for the final scenario, well, we obviously know how this is going to turn out. We're trying to impart a 6,000 low speed vehicle car crash, kind of like slamming it. We're going to leave the localized tactical to we're just kind of trying to scale up into pure mass. We know that for some reason, when we slam it into the, like, let's say, sedan and slam it into it, know how the results we're going to get it's going to be a lot, but right. But what we have to understand is that a car bumper doesn't really, slam as the surface area isn't same with the battering ram and isn't same with the arm fist of either a boxer or an average human being. So we have to increase the surface area. So what you basically do is simulate a downwards rectangular stuff. So basically simulating the area at which the door would cover if it's slammed into it. Right now, to make this realistically, we've already swapped the data out, and then we're not trying to just convert the entire width of the door and make a door bumper. Right now, the result is a total shift from puncturing. Basically, it's a mind-boggling one because take a look at this. Right, it obviously slams through. Right, and then it's funny because why it's funny is this because like I said, simulation assumes it's going to last infinitely, right? But it obviously tells you it's simple. You just look at it and damn, look at the yield strength. Yield strength for this material is 250, and then slamming into it just basically, in my opinion, if you want to reinforce this, now I don't know the amount of reinforcing. Then maybe you try to increase the thickness, make it a vault kind of way, vault standard, like let's say bank vaults thickness. But at this stage, it's totally obliterated. We have a force of about we have a stress value of about 1500, if not 1550, let's say 1550, right? And we've exceeded the entire ultimate structure with the ultimate stress strength of the material, and then basically it's totally destroyed, right? Now when you get a simulation like this, for me, I genuinely think, right, when it comes to simulation, one of the most difficult part in simulation is actually it's the interpretation of the results that actually takes a bit more time than actually the simulator. Now you've done the simulation already, the interpretation of the result, it's not as complex as people make it seem. It is what it is. You see your design, right? And you let them know, okay, this is it. Now, basic stuff now, for instance, common sense. You look at the maximum displacement and you see it's about 16 or 15, 16, right? Yeah, it's about 16 millimeters, right? Now, 16, you obviously know that in reality, this kind of like it exceeds the thickness of the what's it called, the door. So when you see if you imagine a car passing through there, you see it's already slammed into it. The car already passes basically exceeds it, right? So that's it tells you now this 16 there tells you how much the material would actually, let's say, tears, how much the extent of the tear is gonna go, right? If it splits open. You understand my point, right? Because if I don't think if we apply, let's say, it depends on, and now this splitting now totally different depends on how elastic this material is in itself. So it basically doesn't just dent, it just tears open. Okay, now it's kind of interesting to take into account. Like, now let's just have like an overview of what we just did now. Elastic and plastic failure. Elastic basically means if it deforms, it's going to revert back to its original position, right? And then plastic tells you it's going to deform, but it's not going to be able to actually return back to its original position. Now in structural engineering, now we have a 250 megapascal, right? And then what we have to understand is this. Now these four scenarios now shows you how much it actually takes to actually deform a material. The average human being, when you punch at 34 or 35 megapascals, is basically safe. You take the person to the hospital, right? And then when you do with the let's say a martial artist, someone actually trained, it picks at 114, but it still doesn't do it much to a security door, right? People don't go around punching doors, and then you don't want to hurt yourself, take that one to the hospital too. And then military battering, which is actually one of the most advanced way, one of the most physical way people police actually breaks into doors. you slam it and you get a very, very mind-boggling high peak stress of about 632.9, and then obviously there's a failure and there's tears, obviously. And then now, when you now simulate a car or a car, yeah, hitting and slamming, you see the what's it called? Your result is way above as expected, right? Now, the structural optimization here is just allowed to easily handle the absolute peak human performance, managing the deflecting energy, and just trying to show you a relationship between that that force applied. As the force increases, as the trauma increases, you see how it actually gives a actually different what's it called? It gives you a different overview. Now, when you're now matching a 3 millimeter steel, right, against 60,000 Newton vehicle impact, the laws of momentum basically guarantees a structural failure. But you have to understand that this threshold is what allows us to design safer. Okay. Now, when you now designing next time, you have to understand, okay, this is the limit of my material under this condition. This is what will happen under this condition, right? Because you don't want to fix a security door and someone that's very trained just comes and punches your door and your door goes, right? Now, for conclusion, let's start with conclusion one. Mass always wins, right? So while geometry can actually can defeat high velocity human punches, it cannot compensate for raw momentum. Because why this is very important is because during this study, initially, I attempted to actually do the study without the reinforcement at the back. And the human punch basically obliterated it. I mean, the human punch alone at about 800 newtons tore it, and I then realized it's without the reinforcement, it would just be a sheet of metal, right? So then I added the reinforcement, and then the human punch couldn't get through. And then so now, depending on the amount of reinforcement now if I increase the amount of reinforcement, of course I think it's gonna alter the human simulation. It's gonna reduce the stress impacts on it, but it won't really be that significant because no matter what I do, if I increase the reinforcement, it's gonna reduce it. But when you now come down to actually the battering part and then the remaining two scenarios, you have to see that it will take a lot of reinforcement, proper material selection, and then let's say increasing the thickness, and then it won't be just a normal average door. It's just telling you what V like actually is, right? And then our second conclusion is the puncture threshold, right? Material failure occurs at approximately 10 Newton. Below this, we can manage energy. Above this, we can manage destruction. So basically what this means is this, right? If you when we talk about the battering ram, right? The battering ram, people do it. Police officers do it. They slam the door 12,000 pound newtons and it goes, right? I do even think 12,000 newtons is a lot because when you start adding hinges to it, hinges actually fail faster. So what it basically means is the door is gonna fall, the hinges is gonna go off before even the door actually slams through. You understand, right? So basically, at that point, we're now having a situation of okay. But if it was a car, it's absolute destruction. It goes through even if there is a hinge, before the hinge deforms the door, it's already through the door. Okay. Now, design optimization brings you back to my first explanation. The Z drip configures increases the door capacity with over 600 giga. This was something I actually experienced because when I actually did it, it was very, very, very funny to me because I thought, okay, it's a 3 millimeter thick door. And then I simulated a human punch and then boom, it doesn't really make a impact. So I was like, you understand? So yeah. Now, uh this is the end. Thank you very much for staying to the end. Let's build the future together. Thank you for following the series. If you have any question, drop it in the comment section and I'm gonna do my best and I'm gonna reply and I'm gonna explain as much as I can. Okay. Thank you very much. I am Joseph Liston. You can reach me out through my LinkedIn or my LinkedIn, yeah, or my portfolio too. Yeah, the link will be in the description too. So you can just hit me up and have any question and I'm gonna reply. Thank you very much for joining.